Good morning, students. Welcome back to session 8 of linear transformation classes. In the last class, you have studied what's meant by nilpotent transformation and what is the index of nilpotence of a linear transformation, and we have seen that as all the eigenvalues of the nilpotent linear transformations are zeros, so every nilpotent linear transformation can be bring it to triangular form. Okay, and also we have proved two important results in the last class. Among them, the first one is says if v1, v2, etc., vk, if v is the direct sum of v1, v2, etc., vk, where each vi is of dimension ni and is invariant under T, an element of E of V, then a basis of V can be found such that the matrix of T in this basis is of the form A1, 0, 0, etc., 0, A2, and so on, 0, 0, etc., AK, where each AI is an Ni cross Ni matrix and is the matrix of the linear transformation induced by T on Vi. So, if V is the direct sum of these subspaces, then we have this result. Okay. So, and also we have proved another important and big theorem. So, it states, say if T is nilpotent of index of nilpotence n1, then a basis of V can be found such that the matrix of T in this basis has the form mn1 0 etc 0 0 mn2 etc 0 0 0 etc mnr. Here n1 is greater than or equal to n2, greater than or equal to etc greater than or equal to nr, and where n1 plus n2 etc plus nr is equal to dimension of V over F. Okay. So this is one of the important theorem. Means if T is a nilpotent transformation of index of nilpotence n1, then we can find a basis of V such that the matrix of T in this basis is of this form. Here the integers n1, n2, etc., nr are called the invariants of T. These are called the invariants of T. Now let us come to the another definition in this class. Say this definition says, if T belongs to A of V, if T belongs to A of V is nilpotent, then a subspace M of V of dimension M. If T belongs to A of V is nilpotent, then a subspace M of V of dimension M, which is invariant under T, is called cyclic with respect to T. It's called, the subspace M is called cyclic with respect to T if T power of M is 0, T power of M of M is 0, and T power of M minus 1 of M is non-zero. T power of M minus 1 of M is non-zero. Second condition is, there is an element Z in M such that the vectors Z, T of Z, etc. up to T power of M minus 1 of Z, because Tm of M is 0, T power of M minus 1 of Z forms a basis of M. We say the subspace M of V is invariant, which is invariant under is called cyclic with respect to T if this condition holds true, where M is the dimension of M. M is the dimension of the subspace M. So now let's take up the small result, which is stated as a lemma. Say if the subspace M of V of dimension M is cyclic with respect to T, then the dimension of Tk of M is M minus K for all K greater than less than or equal to M. Dimension of Tk of M is M minus K for all K less than or equal to M. So let Z, Tz, T power of M minus 1 of Z be the basis elements of M, because M is of dimension M. So these are M number of basis elements for M. Then what will happen? You multiply all these elements with T power of K, Tk of Z, T power of K plus 1 of Z, etc. In the middle, T minus 1 of Z. Next is Tm of Z comes, that will becomes 0. Okay. So this only forms a basis of Tk of M. Now how many elements are there here? So I start with k. So this means total m elements. I start with k means the remaining elements are m minus k elements. Therefore dimension of the space Tk of m is m minus k. Dimension of Tk of m is m minus k. So that is what we required. Okay. Now I am going to prove another important theorem of this class. So this theorem says two nilpotent linear transformations are similar if and only if they have the same invariants. So this theorem says two nilpotent linear transformations are similar if and only if they have the same invariants. So when you say the linear transformations are similar, if say S and T are two nilpotent linear transformations, if they are assumed to be similar, then T is equal to ST S inverse or S is equal to TS T inverse, right? So that is the definition, you already know it. Okay. So I will consider S and T be two nilpotent linear transformations here. Now suppose T is nilpotent. If T is nilpotent, then by the hypothesis or the things that you have studied in the last class, we can find integers n1 greater than or equal to n2 etc. greater than or equal to nr and subspaces v1, v2 etc. vr of v cyclic with respect to t and of dimensions n1, n2 etc. nr respectively, such that v is the direct sum of v1 plus v2 etc. up to vr. Okay. Now suppose there exists another set of invariants for t, say m1, m2 etc. ms. Are there another set of invariants for the transformation t such that m1 is greater than or equal to m2, greater than or equal to m3 and so on greater than or equal to ms. And subspaces u1, u2 etc. us of v cyclic with respect to t such that v is the direct sum of u1 plus u2 etc. up to us. So v is the direct sum of v1, v2 etc. vr, also v is the direct sum of u1, u2 etc. us. What we have to show? So we have to show these are the same, means we have to show r is same as s and each mi is same as ni, means m1 is equal to n1, m2 is equal to n2 etc. mr is equal to nr. We need to show this. Suppose this is not possible. This is not possible means for some I, mi is not equal to ni. Okay. So it is not possible means at least some elements exist, some numbers exist. So where mi is not equal to ni. So assume that mi is less than ni. Assume that mi is less than ni. Then we have, look here, v as the direct sum of, look here, v as the direct sum of v1, v2 etc. vr. This implies Tmi of v. You apply Tmi of v. This means Tmi of v1, Tmi of v2 etc. Tmi of vr. But each of the vector spaces, v1 is of dimension n1, v2 is of dimension n2 etc. vr is of dimension nr. We have assumed this. Therefore, by the above lemma, what is the dimension of Tmi of v1? So Tmi of v1 is dimension of v1 n1 minus mi. Again, dimension of Tim of v2 is n2 minus mi. Similarly, dimension of Tmi of vr is nr minus mi. Therefore, if we substitute all these values in the above expression, above equation, we get dimension of Tm of v definitely greater than or equal to n1 minus mi plus n2 minus mi etc. plus nr minus mi. You call this by number 1. Call by this number 1. Now v is also the direct sum of u1, u2 etc. us, and as mi is less than ni, we have assumed Tmi of uj certainly will be equal to 0. Tmi of uj certainly is equal to 0 for all j greater than or equal to I. For all j greater than or equal to I. Therefore, what about dimension of vi? Dimension of v becomes Tmi of v becomes Tmi of u1 Tmi of u2 etc. Tmi of ui is 0, ui plus 1 is also 0 up to ui minus 1 exists. Tmi of ui minus 1. This implies dimension of Tmi of v is equal to, what is this? According to the above lemma, m1, because u1 is of dimension m1 minus mi plus m2 minus mi etc. mi minus 1 minus mi. But by our choice of I, first I is the first integer where ni is not equal to mi. Therefore, by choice of I, n1 same as m1, n2 is same as n2 etc. ni minus 1 is same as mi minus 1. Therefore, I can substitute m1 in place of n1, m2 in place of n2 and so on. Therefore, dimension of Tmi of v becomes, say, n1 minus mi, n2 minus mi etc. ni minus 1 minus mi. You call by this number 2. Therefore, from 1 what will happen? So, dimension of Tam of v, 1 says, so this is the 1. So, up to mi minus 1 I can write it as dimension of Tmi of v. So, I will write dimension of Tmi of v is equal to dimension of Tmi of v plus the other integers are ni minus mi plus ni minus mi plus 1 and so on. The last integer is nr minus mi. Okay. So, is this possible? See here, dimension of Tm of is equal to dimension of Tm of v plus some numbers. We have assumed that mi is less than ni, means these are non-zero numbers. This becomes non-zero numbers. Some x is equal to x plus some non-zero number doesn't exist, means which is a contradiction. Why this contradiction arises? We have assumed that ni is not equal to mi for some i. So, we must have ni must be equal to mi for each i. If ni is equal to mi for each i, means what will happen? ni will be equal to mi. Ni will be equal to mi for each i. If ni is equal to mi, then r must be equal to s. R is equal to s means r and s are the invariants, means the invariants n1, n2 etc. nr is same as m1, m2 etc. mr, means the invariants are unique. Thus, what we have proved, if the two nilpotent linear transformations have different invariants, then they cannot be similar, because for their respective matrices, these mn1 0 0 etc. 0 mnr and mn1 mn2 etc. mms, these are cannot be similar. These cannot be similar. Are you understand this? So, these cannot be similar. Conversely, suppose that two nilpotent linear transformations S and T have same invariants n1, n2 etc. nr. Then there are bases by the above theorem. Okay, then there are bases v1, v2 etc. vn and w1, w2 etc. wn of v, such that the matrix of S in v1, v2 etc. vn and the matrix of T in w1, w2 etc. wn are equal to mn1, mn2 etc. mnr. Okay, both the matrix of T and S will be look like this, because if you assume that the invariants are same. Okay, but if I take A is the linear transformation defined on V by A of Vi is equal to Wi, means A is the matrix of change of basis. Okay, A of Vi is equal to Wi, or A is the linear transformation which transform basis Vi is to Wi. Then we can see that S can be written as AT A inverse. S can be written as AT A inverse. Here we represent the matrix by the symbol A itself and the transformation by matrix by the same symbol and the transformation also by the same symbol. So hence S and T are similar. Alright, so now, so if we assume that S and T have the same invariants, then S and T are similar. Thus we have proved two nilpotent linear transformations are similar if and only if they have the same invariants. Okay, that's all for this class. Thank you for listening.